Section 6.2, the standard normal distribution. In Chapter 5, we made the distinction between discrete and continuous random variables. The binomial distribution was a discrete distribution that counted the number of successes from a specific number of trials. And that distribution was discrete because we could only have whole numbers or integers, 1, 2, 5, 10 successes. In this chapter, we're going to concentrate on continuous distributions and specifically the normal distribution. Now, the normal distribution is especially important because a significant number of real situations naturally produce a roughly symmetric bell-shaped curve. Take a look at the following graph. This graph was produced from a sample of 75 men who reported their weight in pounds. Now, keep in mind 75 men or people or whatever is relatively small when you're talking about all people or something to that magnitude. So it's relatively small, but even with this small sample, you can already see a trend. Notice how most of the data values are concentrated in the middle, but tend to trail off in the right tails and left tails. So if we look at this, we see most men, for whatever this sample is representative of, are between 130 or so pounds to 190 to 210, most men. And then if you see in the tails, we have some men that are over that weight, 200 to 10, where some men might be under the weight of 130. So most men fall in that middle category, but as we tend to get to heavier weights or lighter weights, that's when we get smaller values, and we call those the tails. They start to thin out. Well, if we can verify that a data set is approximately normal or bell-shaped like this one, we can calculate various statistics that help with making inferences about the sample or the population or predictions about the future. We've actually already been exposed to the normal distribution with the empirical rule. And recall for bell-shaped data, specifically bell-shaped data, we learned that approximately 68% of the data is contained within one standard deviation of the mean. So either one standard deviation higher than the mean or one standard deviation lower than the mean, and between those two values, we captured 68% of our data. If we went out to 2 standard deviations of the mean, then we captured 95% of our data. And if we went out to 3 standard deviations of the mean, then we captured 99 or 99.7% of our data. So those values are at specific standard deviations, 1, 2, and 3. But we might have something that's 1.25 standard deviations higher than the mean, or negative 0.25 standard deviations below the mean. And we want to still be able to find the area between values such as that. Now be careful that you don't confuse what's going on with the normal distribution with Chebyshev. Chebyshev is just telling us the amount of data between two values for any shaped data. So it can be bell-shaped, it can be skewed negatively, skewed positively, it can have any shape. And Chebyshev is giving us kind of a broader range of how much data is included between two values. But with the empirical rule, we're specifically talking about data that has a nice bell-shaped curve. Okay. Now in this chapter, we're going to expand our knowledge of the percentage of data under the normal curve, as I just talked about, beyond values rather than just 1, 2, or 3 standard deviations within the mean. That curve that we see, that nice smooth curve of the normal distribution, can be defined by the following equation. F of x equal to e to the power -1/2 times x minus mu over sigma, that quantity squared, divided by sigma square root of 2 pi. That's pretty complicated. Now, if we had a specific mu and sigma, so let's say we had some type of distribution where the mean was 2 and the standard deviation was 1. If we knew that about a population and we started to plug in different x values, plug in x equal 1, x equal to 2, x equal to 3, but even smaller values like x equal to 1/2, we would start to get y values that would help us define that nice, smooth, bell-shaped curve. Well, working with that equation is going to be beyond the scope of this course. With a little bit of higher order mathematics, we can show that if mean were 0 and the standard deviation is exactly 1, then the total area under the normal curve is just 1. With these specific values for mu and sigma, so mu equal to 0 and sigma equal to 1, we obtain what's called the standard normal distribution. So the f of x formula above, we could have any mu, any sigma we wanted. The area might not necessarily be equal to 1, but using that formula, we can show that if mu is equal to 0 and sigma is equal to 1, then the area under the curve is exactly equal to 1. Well, right now, we're going to concentrate on finding areas under a standard normal curve between or beyond specific values on the horizontal axis. So initially, we're going to start off with our knowledge of the empirical rule, that's 68, 95, 99 rules that we know. But we're going to also learn how to find these values from a table or using a calculator. Example 1. Refer to the normal curve below to find the following areas. So this one's kind of defined for you. Notice that between -1 and 1, we have two pieces that are 34. Well, if we put those together, there's our 68. And if we add on 13.5 on one side and 13.5 on another side, that's going to give us a total of 95, and so on as we go out into the tails. So we're going to use that picture to find the area under the curve between the given values here. So for part A, we have mu minus sigma, which is here, and mu plus 2 sigma, which is here, and we want the area between those two values. So that means I'm looking at between here and here. Well, all I have to do is add up the chunks. So I have 34% twice, and then 13.5%. And if I sum all of those up, I get 81.5. So between mu minus sigma, which is one standard deviation below the mean, and mu plus 2 sigma, or 2 standard deviations above the mean, the amount of data I capture in between those two values is 81.5%. Okay, take a look at B. To the left of mu plus sigma. Mu plus sigma is right here. And if we want to go to the left of that value, that means we want everything this way. So that means I'm going to add up 0.15, 2.35, 13.5, and then two sections of 34. Let's see what that gives us. And that gives us exactly 84% of our data. And finally, to the right of mu. Well, mu is right in the middle. So that means if I want there we go. So here's that value there, and I want to the right of mu. That means I want all of these values here. So I'm adding up 34 plus 13.5 plus 23, or 2.35 rather, plus 0.15, and that should sum up to 0.5 or 50%. But here's another way to think of it, maybe you already have. Remember we said for the standard normal curve, the total area underneath it is 1. Well, if I'm at the mean, that means I'm right in the middle. And if I just want the area that's to the right of that, I want half of it. So I get 50%. Okay, well, as we mentioned before, sometimes we're going to have values that don't land on exactly one standard deviation or two standard deviations. And we also don't want to express everything in terms of mu and sigma, mu plus sigma, mu minus 2 sigma. So we simplify our values by stating them in terms of the number of standard deviations that the value is away from the mean. So back up to our previous problem, mu minus sigma is 1 standard deviation below the mean, whereas mu plus 2 sigma was 2 standard deviations above the mean. Similarly, this mu plus sigma is 1 standard deviation above the mean. So instead of always saying mu plus sigma, mu minus sigma, we're just going to state a number which tells us how many standard deviations and in which direction that value is away from the mean. Once I get down to those type of numbers, those numbers are called z-scores. We'll use those quite a lot.